Hello, I'm here to present our work on optimizing computer system using structured Bayesian optimization. Our main idea is to leverage system logs combined with expert knowledge to derive meaningful structure and guide the auto-tuning process. My name is Sami and I'm a PhD student in ICOS group here at University of Cambridge. Before starting the talk, it's worth thinking about the landscape of computer system. What are we actually thinking of tuning? So we have general purpose systems such as databases and data processor, and like even computer system architecture design now is done through simulator first before trying them on silicon. So the idea is here is we have these general purpose systems that have many tunable parameters just to meet the end user workloads. To give an idea about how many parameters we are talking about, like we surveyed a couple of different systems. So we have Gem5 Aladdin is a simulator of system architecture accelerator. We have RocksDB, an embedded database. We have Apache Flink, which is a stream processor. Postgres and MySQL are known database management system. As we can see, like a number of parameters simply grow as bigger as more complex the system gets. And by virtue of it having many parameters makes it very like a general purpose, but at the same time, end user needs to tune these parameters to meet their workloads. For example, if they care about the latency in their embedded database, they want to tune the parameters that reduces their latency. The objective is differ from a case to case, and as well as what needs to be tuned, depending on the hardware, depending on the workload, and so on. So with all of this in mind, we definitely need an auto-tuner. This is a tedious process to do for end user, but not any auto-tuner would work. We need auto-tuner that could scale to a large number of parameters. The second thing that's worth thinking about when we're talking about optimizing computer systems is the idea of these computer systems are not like a standard toy problems you would meet in standard machine learning work literature. Here we work with systems that take a long time to even start up. Like it could take from 60 seconds to build a simulator up to 5 minutes to start up a cluster of the systems, and could even take longer depending on how many machines you have in your cluster. Not only starting time is long, you also have the benchmarks or the evaluation or the workload you have. And these could take a very long time. TPC-H, for example, is a very famous benchmark. If you use the factor 20 parameter, you can expect 120-minute evaluation on Postgres. Max speed is the benchmark for simulator for architecture simulation. It takes different workload of computation and memory compute. And these could take 30 minutes. Your YCSB, RocksDB bench, all of them have varying number of varying time to execute, but none of them are like a quick. So in standard machine learning literature, you would often find auto-tuners, but they expect that the evaluation could take less than a minute. So it's very easy to start many experiments. But in computer system, we face this problem of long startup time, long evaluation. Not to mention, starting these systems sometimes could cost and incur financial cost. For example, if you have a cluster on cloud, you probably want to minimize the number of time you have to do the experiments, right? So standard like machine learning methods that tries to just simply keep trying different configurations until it hits the golden configuration is simply ill-suited for this task because it's going to be prohibitively expensive to simply run them and could take forever before it actually finds anything meaningful. And some of these examples are reinforcement learning, hill climbing, evolution strategy, and random search. These are one of the very popular recent methods people are using for tuning. To complicate things even further, often the parameters in computer system depend on each other. For example, you might have a flag that says enable bloom filter and a separate parameter that decides on the size of the bloom filter. Obviously, the second parameter is only meaningful when the flag is enabled. However, this complicated relationship is often overlooked when you are using techniques that do not necessarily respect the hierarchical dependency between the parameters. So with the aforementioned problems, there were recently two very successful approaches proposed to handling this. The idea is you bring an expert and ask them to design a model of the system and the interaction it might face. But this idea is very difficult to generalize to new system as it requires expertise in both the system you are optimizing and ability to actually do probabilistic modeling, which is itself is very difficult process and requires a trial and error to even find correct models about your system. BoGraph is our answer to aforementioned challenges. It's a sample-efficient technique, leveraging both expert knowledge and data to build structure that optimize many parameters in a fewest number of evaluation. First, it takes in any expert provided knowledge, for example, the objective you want to optimize, for example, latency, the parameter space, the parameters you want to tune and their values, and any structure you want to optimize. But then BoGraph grabs that representation and build a graph model representing dependency of inner component of the system. These are stuff you have not provided as an expert. It discovers them by parsing the logs and building a causal structure um, of the dependency of the inner working of the system against the parameters and the objective. And then finally produce a probabilistic graphical model that is consumed by the next component in the system in BoGraph, which is BoTorch. BoTorch is a library that allows you to optimize a sample and optimize any probabilistic model you have, and allows by optimizing it, you find optimal configuration to try on the real system. And finally, when you get the optimal configuration, you give them back to the system, and the system evaluate them and give a return to BoGraph the results as well as the logs, so to allow it to basically reiterate and build the next optimal configuration. So we focus now on BoGraph and look at its inner working. BoGraph is built on the idea of Bayesian optimization. Rather than optimizing the system directly, you build a model of the system first, then explore potential configuration on the model before trying it on the real system. Thus, you reduce the number needed of evaluation needed on the real system. First, the main idea of BoGraph is leveraging context to break down complicated models, which allow you to model many more parameters and using less data. So, for example, on the right, if you don't have a context, you need to consider all the parameters all the time whenever you are modeling an objective. So if your objective is y here, you need to consider 5 different parameters impacting it. But on the left, we break down the model structure by introducing two intermediate nodes. These are the in BoGraph found by leveraging the logs. These intermediate nodes break down the dependency, and now your y, which is the objective, for example, latency, only depends on z1 and z2, rather than on all the x5s. This allows you to have interpretive model, allows you to understand what's happening in your tuning process, also feed you back some knowledge about your data system, and finally allows you to tune more parameters quicker and faster. This process, so the way it builds this structure involves parsing, cleaning the logs, processing it, and then performing structural learning before adding any expert knowledge and producing a directed acyclic graph. This directly acyclic graph represents statistical dependency between components, and then finally can transfer that DAG into a probabilistic DAG that we can sample and generate a new prediction from it. We will use a running example from Gen 5 Aladdin. It's a case study we have performed on system architecture simulation design and show the pipeline of BoGraph. So the first step is parsing the logs. So one of the common questions we have is how will this transform to a different system? So we've done experiments on Gen 5, PostgreSQL, and RocksDB, and in general, these systems tend to provide logs in a nice way, where it's expected these logs are used by some monitoring and health system down the road anyway, because that's how you make sure your system is running in a healthy way. We leverage the exact same infrastructure that people already use for the monitoring and site reliability engineering to make sure that to find meaningful structure that impacts the objective of your system. So we get these logs. They tell you different part about the system. For example, on the left side you have Gen 5. You know which component of the CPU. So the cache in the CPU is receiving 5,800 span pages. This information, there's like 1,000 different metrics. While it's useful in a very condensed way for an expert, we can't possibly just use that as it is. So we have to process it before we use and automate the process of extracting information from here. And this is where BoGraph shines. So we grab these logs, we transform them into to the right side, which is a clean representation that can use various optimization technique. The main idea here is we grab them, we clean out any uninformative metrics, for example, any metric that doesn't change between different experiments. We standardize them to make sure that the large the unit doesn't matter between them. So you don't have something that uses large units overshadowing something that doesn't use many units, a smaller unit. And then we also group related metrics together. So this grouping, we have two configurable options. So either you use a clustering algorithm, which is an approximation and not ideal most of the time, or you could introduce some type of hinting, which is in Gem 5 and Postgres is very simple to do because the name of the metric itself gives you an idea what type of cluster it should be in. In Gem 5, for example, everything under CPU is tagged with CPU, everything under your mem control is tagged under mem control already in the name of the metric. So we use the same idea, and this is a simple regexpression expression that allows you to group related metric together. Once we group them together, we now reduces them using a like a principle. We use factor analysis, similar some technique similar to PCA that reduces the dimensionality um, of the feature. And finally, we transform this clean data set into a structure using causal structural learning literature. In the recent 2-3 years, there was an explosion of the idea of using continuous learning to find a causal structure. This idea makes transform this causal structural learning from intractable problem to a tractable with a very fast solution by approximating it into a continuous function of minimization. What I'm trying to say here is this technique would not have been possible 4 years ago, but now with the new approaches of causal structural learning, we can transform this into a continuous optimization function and leverage all the advantages of PyTorch and TensorFlow to basically make this run very fast and learn the causal structure on the right. The way it's done is you try to find a scoring function that scores the graph with the log likelihood of the graph. So which graph explains your data the most, but also penalizes the graphs that are too complicated. So you don't want a graph that explains anything. You want a graph that is the simplest but explains your data the most. There are various small details here that I'm skipping over because that's part of our contribution. It's mostly from Notier's paper. I've cited here in the bottom. I highly recommend following that for more about causal structural learning. Finally, we produce this structure, and it has a statistical dependency. It captures the statistical dependency of the component in the system. But while this is useful, it's not something you could still generate samples from. It's not something you could use to optimize and run standard Bayesian optimization techniques. So we try to transform it into a probabilistic graphical model that allows you to generate samples before interacting with the system directly. So here, for each node we have in this dependency graph, we transform it into a probabilistic one using Gaussian process, or if a user provide a model, an expert driven model, we could inject it at this stage as well. And then we train each node in the graph independently, so this allows you to scale to as many machines as you want to do the training. But during inference, there is slightly something tricky. So we can't simply generate samples from a probabilistic graphical model by simply duct taping things together. When you have a posterior of the Gaussian process, for example, in average power, this posterior can't be conditioned on in the ATP case here on the right. Simply because this conditioning is intractable. Now you need to condition over all possible parameter of the posterior previously, which is intractable. Instead, what we do is we approximate that by generating many samples from each node in the graph, and then we condition on the sample rather than on the whole posterior. The more samples you have, the more accurate representation of the posterior you get. And obviously, it takes longer to generate these samples. We use samplers from BoTorch library, as well as their quasi-acquisition function to optimize over the samples. So standard Bayesian optimization technique tries to find a closed form solutions that minimizes the objective straight from the posterior of your model. But in this case, because we have a complicated posterior, we can't have a closed form solution. So instead, we sample many samples, and then we use the utility function, the acquisition function, to optimize over the samples. This is possible because of ProTouch. Again, we cite the paper and highly recommend following that very interesting work. Next, we talk about the evaluation and how we evaluated BoGraph. So we optimized the design parameters of system accelerator Gen5 Alabed by tuning all the 20 parameters that are exposed in the simulator, and these have 2 to the power 64 unique design combination, making a standard technique of using a parameter sweeper just impossible to use. And we benchmarked it using max suite benchmark. It's a mix of the data and compute workloads, very standard to use in computer system architecture design. And then we also optimized the EDP function, which is the energy delay product. Again, this is a very standard objective to minimize in this computer system design, which basically reduces your energy consumption while provide you with the faster system. So the first thing we can notice is BoGraph finds better configuration than any other autotuner that we have tried, and it finds them in in every single task of the benchmark. These results coming from after 100 evaluation, and the higher the ADP, the better. And the y-axis is the X factor improvement over default. So we can see sometime BoGraph finds up to 7 better EDP than standard default settings. And not only that, BoGraph finds these the optimized parameters quicker and more robustly than other methods. So we can see in just 20 steps, it already found configurations that took the next best method, BoTosh, 100 steps to even get closer to. And this idea of faster conversion is the core principle we use here to motivate BoGraph. So leveraging both expert knowledge and data could lead to faster conversion, quicker and better. While we evaluated on Gem5, we also working currently on PostgreSQL and RocksDB case studies already on Postgres, having very promising results. BoGraph itself could be applied to anything that reports metrics and logs to end user. For example, any of the stream processors, we looked at the logs and they seem good enough for BoGraph to find meaningful structure. We could also potentially look at any system that provide a lot of data that is not currently used by your model, by your autotuner. BoGraph could potentially learn models that could help optimize your system. In summary, we presented BoGraph, a framework that can leverage both expert knowledge and logs to basically derive a meaningful structure to tune and optimize your system in a fewest number of evaluation. The key takeaway is logs contain very useful information to decompose the system for tuning purposes. So by leveraging that, you could tune more parameters and quickly. And by allowing the user to inject their knowledge through the use of an API, which we didn't show in this talk, but it is in the paper, and combining that with the logs discovery, you could lead to faster conversions and find better configuration. I hope the talk was interesting. If you have any questions, send me a message on Slack or email me at my email here in the bottom. Have a good rest of the day. Thank you.